Oh, there you are. I know. So good morning, everybody. Today we will discuss the bracketing technique, which is a very clever procedure, mathematical procedure that allows us to compute various perturbation theory orders for the wave function and energy very efficiently, very quickly. Okay, and when we're done with this, we'll go back to MBPT and we'll start applying what we know about perturbation theory to the Many-Fermion correlation problem. But before I go on, let me briefly summarize the content of the last lecture, because I'll need some of this information. So we are discussing the perturbative approach to the Hermitian eigenvalue problem for a non-degenerate state psi node, which typically is the ground state. And we worked out the expressions that tell us that psi node can be represented as a sum of perturbative corrections. We're summing here over n from 0 to infinity, okay, where the zeroth order correction is simply phi 0, and phi 0 is an eigenstate of the unperturbed operator k0. And then we have perturbative corrections that we can extract from a series that we developed, which uses the reduced resolvent of the unperturbed operator k0, called R0. Okay, so what we have there is R0 W prime to the n, then we have R0 W acting on phi 0. Okay? And the quantity W prime, which we are defined, which we have to use here, is simply the perturbation operator W minus K0 minus kappa 0. Okay? Which, given the fact that we have a perturbative series for K0 as well, and kappa 0 is the zero order approximation to K0, is simply W minus the sum of K0 M, where M runs from 1 to infinity. In other words, we have the operator W prime, which is the perturbation operator W, which we obtain when we split K into K0 and W. And then we have, we also have then corrections beginning with the first order. So in other words, W prime is not just the first order expression. It is actually mixing different orders, and that's something you have to watch closely, right, when you are trying to extract various perturbation theory orders from this series. Good morning. And then obviously we have an analogous expansion for the eigenvalue K0. So we obtain a sum of various corrections, various perturbation theory orders, running from 0 to infinity. So the zeroth order correction is kappa 0, the eigenvalue that corresponds to phi 0. Okay? So that's the zeroth order correction, or the zeroth order approximation to K0. And then we have the first order, which is an expectation value of phi of the perturbation operator W. And then we have second and higher orders buried in a series which looks as follows. We have phi 0 W R 0 W prime to the n. Then we have R 0 W phi 0. Okay, so we have this very nice structure: zeroth order, first order, second and higher orders here. Okay. And you know, we worked these expressions out for low orders. We considered wave function corrections to the third order. That's pretty high. And we considered energy corrections or eigenvalue corrections through fourth order. Today we'll discuss how to generate them more efficiently. Okay, and in doing so, we notice several interesting observation things. For example, we notice that if you look at the correction in order n plus 1, correction to the eigenvalue k0 in order n plus 1, you can generate it from the knowledge of the nth order correction to the wave function. Okay, and that's the expression we will use. I also talked about the Wigner's 2n plus 1 rule, but we will not use it here too much, so I will not discuss it right now. Okay. And then another observation that we made is that if you look at these perturbative corrections, they always seem to have this interesting structure. So if you look at the nth order correction to the wave function, okay, what it has is it has the sort of the leading term, which is R0W to the n acting on T0, and then it has these various other terms, which seem to be various combinations of W's and R0s with brackets in them representing expectation values in T0. So we'll talk about it today. And we also notice that in a similar way, if you look at the correction to K0 in order n plus 1, then there's a leading term which has a very well-defined structure, W, R0, W to the n, T0. So n orders come from W, R0W in nth power, and then you have another W, so that's why we have order n plus 1 over here. And then there are these other terms, okay, which we have to learn how to extract. As I said, we did it last time for the lowest few orders. We would like to have a procedure that allows us to do it in any order very quickly. Okay. Maybe one comment I would like to make that these other terms, okay, if you really look closely where they come from, you remember they came from the fact that W prime is not just W. If W prime was just W, you would just stop here. It would be a very simple theory. Okay, that would be Rayleigh-Schrödinger perturbation theory. Okay, but because our W prime is shifted, and in the process of working things out, we had to take into consideration all these corrections to K0 in W prime, and that produced all these other terms. Okay, more and more as you go to higher orders. As you remember in this set, there was nothing in the lower orders, but then eventually you started seeing lots of terms there. Okay, and then at the end of the last lecture, I demonstrated that the reduced resolvent R0 has a spectral representation that looks like this: phi n over kappa 0 minus kappa n. We sum over n from over n, avoiding of course the singularity, that is the n equals 0 term. All right, and the phi n's here are eigenstates of the unperturbed operator. Okay, this is of course something we know because we in perturbation theory we make the assumption that we know all eigenstates of and all eigenvalues of K0. All right. Of course, in practice, if you don't know all of them, suppose you know some number of them, a lowest certain number of them, right? Well, then of course you can try to approximate the resolvent, okay? And then you may wonder whether that resolvent is well, approximated well enough, right? In your considerations. But that's the fact that we are assuming that you need to know all of them doesn't really prevent us from making various approximations. But I will not talk about these approximations, certainly not right now. Okay. So I promised you last time that we will start today's lecture by simply using this spectral representation of the reduced resolvent to simply see how the perturbative corrections to the wave function energy look like. Very explicitly now, as explicitly almost as you can make them. Okay, so let's start doing this. So suppose I would like to know what is the most explicit form of the first order correction to the wave function. You remember we proved last time that it is R0W acting on phi0. So that's a sort of an abstract definition of it where, okay, we know what W is, but R0 is still written as an abstract operator. Okay, we know its definition, but it's not the definition you would apply in computations. You know, what is more, if you want to have working weight expressions for computations, then you have to use this form, because then we know pns and we know kappa n's. So, you know, I'm going to do it right now. We have a summation over n, different than 0. We have phi n over kappa 0 minus kappa n. Okay, that's the resolvent part. Then you have w. Okay, so I'll just continue. I'll put w here, and then you have phi 0. Okay, and you see I'm done. And as you can see, that's the famous correction to, you know, I mean, I don't know, how many of you have seen first order correction as a wave function? Yeah, good. Yeah, this is sort of, you know, it is not always being taught in undergraduate classes, depends, you know, what the instructors do about this, but, you know, certainly if you want to talk about perturbational theory in some sort of at some undergraduate level, you certainly should show this expression, because that's the lowest order you've got, right? I would say going to second order, that would probably not be a typical undergraduate knowledge, but, you know, but the first order is certainly worth looking at. And you can see we have it. But you look, I would like to appreciate how quickly we got it. We just got it by writing things, you know, from definitions. I didn't do any manipulations anymore, because I'm done with manipulations. You know, we spent the last 2 lectures, or 3 lectures, right, manipulating perturbation theory in general, okay? And please note, so what you see here is, you can see what you have here is that linear, it's an expansion in terms of phi n's, and what I put here in this red zone, there are some coefficients, right? Say, let's call them Cn1. First order, you know, that you can calculate, you can see from the matrix elements of W and the perturbative denominators, okay? And please note that we are avoiding n equals 0, meaning that our correction is in the Q space. Okay? And that, of course, will be true for every other order, because if you really go back to our orders, you know, to this expression over there, let's see, okay, this one, you see, it starts with R0. The leftmost operator is R0. R0 operates in the Q space, which means that the perturbation theory has a beautiful mathematical structure. Phi 0 is the P space part, and the, you know, and corrections take care of the Q space. That is, you know, they care of all these unperturbed states which are orthogonal to phi 0. Okay. All right. Okay. So let's. Well, if this is so easy, then let's go to the next order, I guess, and see what we can learn about it. So second order. You know, as you remember, we derived an expression for it that looks like this. It's R0, W, R0, W phi 0. That's the leading term. Okay? You know, this is what we wrote before as R0 W squared. I just wrote it now more explicitly. Okay, and then there is another term, which is an expectation value of W times R0 squared W phi 0. Okay? So again, you know, if you want to work out the explicit expression, we're going to replace each of these R0s by their spectral representation. So we end up with sum over, say, m different than 0, phi m divided by kappa 0 minus kappa m. Okay, that's the first result that I have here. Then I have the W. I will write it like this so you really can see what I'm doing about it. Then I have the next R0. Okay, I'm not going to use symbol M anymore, because, you know, those two summations are independent. And I remember I made these comments a long time ago that you always have to watch out for what symbols you are using in your calculations, right? You know, it is tempting to use the same symbol because I say n here. No, you cannot use n here and n here, because this summation and that summation are independent. Okay, so we have to use some other symbols. So I'm going to use n here and n here. All right. So then I have phi n over kappa 0 minus kappa n. That's the second copy of the resolvent. Then I have another w, and then I have phi 0. Okay. So we'll have to work on this. All right. We'll do it in a second. All right. Well, then what I have is minus an expectation value of W, and then you have square of the resolvent. Well, let's try to do that. So again, I'll write it as two summations, sum over m different than 0, phi m for the first resolvent, and then I will have sum over n different than 0, phi n over kappa 0 minus kappa n for the second resolvent. So now I have R0 squared taken care of. Then I have the W, and then I act on phi 0. Okay? Well, that's what what you get. Let's now try to polish this expression a little bit. So what is then psi 0 to the second order correction to the wave function? All right. Well, you can see you just have to you can see there's going to be a double summation over m and n, avoiding phi 0. So it's going to be a summation over m n different than 0. In some books, what people do, they don't write that. They don't write different than 0. They put a prime. By putting that prime in the summation, the author of the book, or the authors of the book, are trying to tell you avoid m n equals 0. Okay? I'm not going to do this, but certainly we could. Okay? I just don't need to. I don't want to introduce, too many people already have many symbols for various things, so let's not introduce yet another one for no apparent reason. Okay? So then what we have there, let's just read it. It's a very simple procedure. You can see it's phi m. Okay? We start from here. Phi m. Then there's phi m w phi n. So that's a matrix element of the W. Okay? Okay? So now you arrive here. Then you have phi n W phi 0. That's another matrix element. Okay, and I'm done with what's in the numerator. Well, let's see. The denominator is, of course, the product of two perturbative denominators, kappa 0 minus kappa n times kappa 0 minus kappa n. Okay, and we are done with the leading term. Okay, you can see that it has this beautiful structure again. Which is very characteristic of perturbation theory. Okay, you have a product of perturbation theory denominators. Okay, and then you have, in the numerator, you have matrix elements of the perturbation operator. And you can kind of read it from the right. Actually, I recommend that sometimes you think that way. You start from phi 0, go into phi n. You go from phi n to phi n. So phi n is sort of an intermediate sort of level, okay? And we'll see that this actually level of understanding will help us out in the MBPT when we start sort of giving various MBPT corrections to the wave function and energy, their physical interpretation. Well, let's look at the second term. Well, that's an interesting one. Because, you see, what you have here, you don't have that W in the middle. You have resolvent running into resolvent, which means that you have phi m running into phi n directly. But, phi m, the phi n's are orthonormal. So phi m, phi n, inner product of it is canonical delta. Okay? So what you really see here, when I start writing, is a double summation. You have phi m here, you have phi n there, but in the middle you have a canonical delta. Okay? So you can see that when I have this, you have phi m running into phi n, so you have delta mn. That canonical delta will eliminate, will shrink the double summation to a single summation, right? Instead of summing over m's and n's, you will sum over m equal n. Okay? So because of this, the second term looks like this. It's an expectation value of phi of w times a summation over n, say, different than 0. Okay? And then what you see is phi n, the middle part is gone, because phi m, phi n will be canonical delta. The delta will shrink the double summation to a single one. So you will have the phi m, okay? And okay, I'm going to call it n. So it's going to be phi n and then phi n here. So we're going to have the projection operator. Squeeze it. And then you are here. Well, then you have a W and then you have phi 0. So you finish this by creating a matrix element. Phi n, W, phi 0, okay? And then in the denominator, because m equals n, we'll have a square of the denominator, okay? And that's it, okay? And once again, you can see in this representation, okay, this correcting term that corrects the leading term, is also an expansion in terms of phi n's, okay? And the matrix elements, the coefficients at these phi n's are simply, you can see where they are. This part, we have to take this and multiply by that and put aside. Okay, so if you want to know the coefficient of a specific phi n, it's very easy for you to extract it from this. Okay. One thing that we've learned in the process of doing so, okay, is that, please note that what I was really doing, I was trying to learn what is the square of the resolvent. Now, this middle part here, this is a resolvent, that's another resolvent, right? You can see what happens when you square the resolvent, you know, there's going to be this delta in the middle. That means that in order to compute the square of the resolvent, it's a very simple procedure. Square of the resolvent is simply a sum over n different than 0, phi n divided by the square of the denominator, okay? You see? Is this clear to everybody? You know, it's really here. Okay, you have phi, then the middle part, phi n, and doing the middle part, which will be canonical delta. Then we reduce the two summations to a single one. So that means that all you will have to do is to pick up the first, the cat, the brown, and divide by the square of the denominator. And that's what I did. Okay? Well, you know, I guess by the same argument, you can clearly see that if I want to know what is the kth power of the resolvent, and we'll certainly need that at some point, okay, because, you know, the higher the order, the more of these are R0s you have, well then, you know, the rule is very simple. You know, it's not like this resolvent is such a complex object that, you know, that the initial definition sort of implies, right? All you need to do is to simply write the projection operator phi n in the numerator and divide by the kth power of the perturbative denominator and sum over n different 0. So in other words, the power of the resolvent looks like the original definition, except that you have to compute the power, the corresponding power of the denominator, and you're done. Okay, a very nice thing to notice. Please remember about it. Okay, so we can go then to size 03. I'm not going to do it. I think you can do it yourself. I encourage you to do it so that you sort of learn how these things look like. But I would say I wouldn't recommend necessarily that you work out the 10th order because there is no purpose unless you really need it for some of your sort of research or something like this. Then I would not do it necessarily right now. Okay, but the procedure, as you can see, is extremely straightforward. We have perturbation orders. We have R0. We just stick R0 in its spectral form, and we're done. So it's no longer like a multi-page derivation of each order, okay? And if you look at the perturbative corrections, of course, you know, this is a different situation because the first order correction does not require R0, so I'm going to just copy what we know about it. It's just an expectation value of W, okay, as we proved last time. And as you can still see here in this expansion, there is phi 0, W phi 0 here as the first order. So let's look at the lowest order that has R0, okay? That's the second order. And, second order is phi 0, W, R0, W phi 0. And I think I asked you last time whether you have seen the equation. Some of you said, well, maybe yes, maybe no. Okay, well, so how about that one? I'll now stick the R0 from our spectral representation, okay? What happens is, the summation over n different than 0, you have phi 0, W, okay? Maybe I'll be marking this with a color. So, we have this part. Well, that's here, okay? Then you have, from R0 you get phi n, okay? That's the resolvent part. And then we have you have to finish it off with W phi 0 in the right part of our expression, okay? So that's what you get. Maybe I'll erase now this because I think it's obvious. And then we derive it, we divide it by what's in the resolvent, kappa 0 minus kappa n. Okay? And this is the famous formula for the second order correction to the energy. Right? Have you seen that? You must have. For people in chemistry, if you want to know what dispersion forces are, London dispersion forces, well, that's how you define them, through this correction, okay? W then is, is the interaction potential between, let's say, two molecules, right? And then, the dispersion and induction forces, come from this, okay? And of course, we'll see what this does in MBPT. But anyway, you can also see the logic of this expression. And I would like you to pay attention to the logic. Say, start from here. Through W, you go to some intermediate state, and then you return back to phi0. So you can easily imagine that if it's the third order, I'll be doing this more times. I've got to go from phi0 to some phi(n), from phi(n) to some phi(m), from some phi(m) to something or whatever, and then eventually end up with phi0. But you go through a sequence of intermediate states. That's a very characteristic feature of perturbation theory, okay? Because there's a lot of physics in those intermediate states, and we'll discuss that. Okay, so now that we know this stuff, then let's talk about the bracketing technique. Okay? All right, when I go back to these initial summary statements, we already noticed that if you look at the nth order correction of the wave function, it has the leading term, which is always R0W to the power corresponding to the order, plus some sort of other terms that we have to learn how to generate quickly. We know how to generate them from this series, but of course we would like to do it even quicker. And then for the n plus first order correction to the energy, we again have this leading term and the corrections. So let me maybe copy this information in here and introduce the proper terminology. Okay? So the nth order correction to the wave function is the leading term plus the other terms. Now, we're going to call the leading term the principal term. Okay? And that term is very important to remember because I'll be using it when I start going into Linker-Pasteur theorem and all these things. We'll be talking about principal term and these other terms. How do we call these other terms? They are usually called renormalization terms. These renormalization terms, as you remember, they appear to have various mixtures of W's and R0s, okay, that seem to be obtained by inserting brackets representing mean value in phi0 into the principal term. They seem to have this structure, and that's the structure we'll try to discuss today. Therefore, the energy corrections in order n plus 1, okay, we would have again the principal term, which is R0W to the n, and then we have again renormalization terms. Okay? So we use the same terminology. The leading term is called the principal term. You just have to say it's in the energy or in the eigenvalue, right? And then you have renormalization terms that go with it. Okay? And this is of course true for n equals 0, 1, and so on. Okay? So now the thing is, okay, we know what is the principal term, always, that's easy. We need to figure some quick procedure to get the renormalization terms. Okay? So that you can do your homework, for example. Okay? Well, let's try to do this. In order to do this, let me first introduce a sort of a compact notation. Instead of writing expectation values of operators in phi0, okay, I'll just drop phi0s and I'll just write the pair of brackets, okay? Because the bracketing technique really is what the name says. It's playing with the brackets. Okay, so we'll be playing with the brackets. Okay, inserting them in various ways. All right. So in other words, from now on, at least for some time, at least, when I write something like this, what I really mean by that is an expectation value of W in phi0. Okay. So when you see something like this, WR0W is another example. Okay. What I really will mean by this is phi0 W R0 W phi0. Okay. You obviously recognize that this is the first order correction to the energy, and this is the second order correction to the energy that we just worked out. Okay. But in this notation, it's a sort of more compact. Okay? And of course you can produce yourself more examples if you like. With this notation, our various corrections to energy or to the eigenvalue K0 will look like this. I already showed you how the lowest two look like. Okay, so we know now that in this new notation, the first order correction is simply the bracketed W. The second order correction is the bracketed W, R0, W. So then what is the third order correction? If you look back at your lecture notes, okay, it is going to be the principal term, which is W. Then you have R0, W cubed, squared, okay? That's the principal term. Okay? This bracket here means phi0 here. And then you have to subtract the renormalization, then you have to correct it with the renormalization term, which comes with a minus, which is the expectation value of W in phi0 times W R0 squared W. Okay? So you see, it sort of looks a little bit neater compared to what we've been writing so far. Okay? Let me write one more, K04, because I'll be using these as examples today. Okay? So the fourth order is, what you have is the cube of R0W multiplying W and then bracketed with phi0. Okay? And then you have various normalization terms. The first one is expectation value of W times W R0 squared W R0 W plus its companion term, where the first resolvent is in the first power and the second one comes with a square. Okay, so that's the one contribution. Then we have plus the square of the expectation value of W times W R0 square W. Okay, and then the last term is minus W R0 W and then W R0 square W. Okay, and you'll do the fifth one. Okay, in your homework. Okay, but you can see that that when we use this compact this bracket notation where we don't write phi0s, it sort of looks a little bit nicer. Okay, I guess, right? And of course, I could do this similar. I could write similar equations for the wave function correction. I'm not going to do it now. I'll come back to wave function corrections later. Let's start with a procedure that allows us to generate these various expressions quickly. Okay, by inserting brackets into the principal term. That procedure is called the bracketing technique. Okay? This technique, the idea of bracketing actually was first noticed by Brueckner. When Brueckner was working on MBPT in the late 50s, he already noticed that if you look at the low orders, okay, essentially you can obtain them by starting with the principal term and inserting brackets representing mean value in phi0 into this principal term. But he used it. He proposed Linker-Kessler theorem. Goldstone proved Linker-Kessler theorem, but there was no formal proof at that time that what Brueckner noticed in the low orders is true in any order. That was actually proved a little bit later, okay, by Huby. This was in 1961. It's a beautiful paper in Proceedings of the Physical Society, okay, that simply proves that you can have a very simple set of rules for generating various perturbative corrections. So what's the idea? Well, the idea is that we produce renormalization terms. Of course, we always know how to write the principal term, okay? And then in order to figure the renormalization terms, so I'm going to be focusing on the renormalization terms right now in energy. Okay, if I want to do this, Then what I need to do, I need to simply start with the principal term. Which is W, and then you have n copies of R0W. So you start with the principal term and then you insert brackets. Insert brackets or pairs of brackets representing the mean value, like I said, okay, into the principal term. Okay? Of course, there are rules about how you do this. Brackets, or these bracket pairs, must be non-straddling but one can have say a bracket pair inside another pair. Okay? So in other words, you can't do something like this. You know, if I have, say, two brackets, I can have something like this. I can, you know, but I cannot have this. Sort of like, you know, one pair of brackets is this, and the other one is sort of trying to pull it. Okay? That cannot happen. Okay? So that's the word non-straddling, I guess, in this definition. So that is not allowed. Okay? So I'll erase it because I think so we'll be seeing more in it soon. Okay? But that's not everything, you know. So what you do, what we're going to be doing is, let's see, maybe I'll still keep these expressions. Let's go here. So we'll be inserting these non-straddling bracket pairs into the principal term, okay? And these inserted brackets have to follow the following three additional rules, okay? I'll write them as rules 1 through 3, I guess. All right? So, no two brackets can touch. Okay? Let me first list those rules and then I'll explain. Second rule. Bracketing of the leftmost and rightmost W, perturbation operator, is not permitted. Okay? And then the next point is that each bracket pair must have the W operator or operators on each side. In other words, what you have to have is when you put this bracket inside the principal term, that bracket has to have W at this end, W at that end, and of course things in between maybe, okay? But you cannot have, say, resolvent here, or resolvent here. You can't do it. Okay, so that's what this rule says, and we'll see to it then. Okay, so what you do is this. You start with a principal term, insert pairs of non-straddling brackets, okay, into the principal term, okay? And then you just have to make sure that you have to do it in all possible ways, and you have to make sure that no two brackets can touch. Bracketing of the leftmost and the rightmost W is simply not allowed, and then each bracket pair must have a structure where you have one W on one side, W on another side, and you can have something in between. Of course, you can only have single W, that's okay. Okay, then you have just one W, right? But you cannot have resolvent in the at the bracket. That's not allowed. Okay. So let's now practice this, and through that practice, I'll be pointing, out all these, these rules. Okay, while explaining why you would never try to violate them. Simple violation of these rules will lead to problems. But of course, before I do this, there's another issue. What is the sign? You remember these renormalization terms? You still have them in the blackboard. They come sometimes with a plus, sometimes with a minus. How do you know? Okay, well, there's a simple rule that Huby actually also derived in his wonderful paper. Beautiful paper. Okay, really fantastic paper. The fact that you can prove such things in any order is just remarkable. Okay, so what is the rule for the sign? The sign is defined as -1 to the r, where r is the number of inserted bracket pairs. Okay? Okay, so now we have the complete set of rules. Let's start working out some examples and then talking about this. Okay, so I'm going to start with the third order. I'm not going to look at the first order or second order. In the first order, there is really nothing to do. You can see it there, just one W inside the bracket, so you can't squeeze more brackets into it. If you look at the second order, also there is nothing I can do really, because I would have to bracket the leftmost or rightmost W's, and I'm not allowed to do this, so I'm not going to do that. And there is no renormalization terms, as you can see as a result. You can already see why is it that K02 has no renormalization terms. It doesn't, because you cannot bracket anything in it. So the lowest order where you can do some interesting work is the third order. So let's do that. Okay, how about K03? Okay, so let me start with the principal term. Okay, so the principal term. Principal term is W, R0, W, R0, W. Okay, you always have to start in this expanded form. Don't write it as R0, W squared, for example, because you would not be able to see things through. You really have to write it in an expanded form. Okay, and then what I'll do is this. I'll start introducing these various bracket pairs. Okay, but in order to really explain this hopefully well, okay, I will first assume that I haven't heard about these rules. So I will sort of pretend like I know that I have to insert brackets, but I will sort of not pay attention to the rules yet, and I'll show you why these rules have to be obeyed. Okay, so we'll have that. So imagine that I want to insert brackets into this, representing mean values of operators, okay, in various ways. Well, let's start surrounding one operator, okay, with the brackets first, sort of as a sort of training exercise. Well, we have 5 operators, so there should be 5 cases. Okay, so let me start writing maybe at this blackboard, because so then we have all of this on the one blackboard. So you write. So I'm going to actually write 5 copies right away, maybe, of this expression. Okay, so we have 3 W's mixed up with 2 R0s. Okay. Okay, the 5th one here, right? I'll put this up later when I'm done. Okay? So I have 5. I wrote 5 copies of the principal term because I have 5 operators, so I have to. Something wrong? No? Okay. Alright. And then I'll start putting in brackets. Maybe I'll use color to do this. Okay? So I will be surrounding one operator, okay, in each case. So I can surround the first W. I can try to surround the resolvent. As I said, right now I'm pretending that I don't know the rules. So I'm just naively putting these brackets in. Okay? Then I surround the middle W. Then I'll surround this R0, and I'll surround the W here. The last one. Okay? Well, let's try to read this. Well, what is the first term? We know that this bracket means expectation value, so it's a number. So you can take it out. So you end up with W times R0, W, R0, W. You see, that expression makes no sense. Because, you remember, what is the meaning of the bracket? There is phi 0 here, which we are not writing. So what you really see here, in this region, okay, is phi 0, R0. That's what's there. Right? But the resolvent, because of the Q operator in it, eliminates phi 0. Okay? So we know that this can't work. Okay? We know that this is 0. So that means that this term has no meaning to us. Okay? You can write it, but you know that it's not going to play any role. So we can now call these cases A through E. Okay? So we know that A, okay, not possible. Now let's see why is it not possible because of our rules. Well, what do our rules say? Our rules says that you cannot surround the leftmost or rightmost W. You cannot bracket, you know. Well, I tried and I failed. That means that the rule seems okay. Alright? Well, let's look at the next step. Well, here, I would have to take the expectation value of R0 out. Okay? And then you end up with W square R0 W. Once again, that is a no-go because expectation value of R0 is 0. Remember, this expectation value here is really an expectation value in phi 0. That's what the bracket means. And we know that R0 acting on either side of the bracket will give you 0. Okay? Meaning that this doesn't go anywhere. What is the rule that we're violating here? Well, that is a rule. So actually, maybe I should, let's see, I have these rules. Bracketing of the levels. Yeah, so here, this cannot work because of rule 1. Okay? Here, you can see that we are, we said in rule 2 that each bracket must have W. Okay, on each side. Well, it doesn't. There's no W here. So we violated the rule and we failed. But now you understand why we failed. Why we have that rule. Okay? So that means that this is a no-go. Well, what about the next one? Well, here I take an expectation value of the W out, and then I end up with W R0 squared W. Well, this one looks okay. There's no reason for us to eliminate it because W is acting on phi 0 will produce something, depending on what W is, okay? And it is a legitimate expression. If you look at our rules, our bracket here has W's on each side. That are also, okay, meaning that we didn't break any rules. So we're going to keep it. And the next one, of course, the next two are analogs of A and B, okay? So the next one, for example, would be an expectation value of R0, okay, times W, R0, W squared, okay? And then, of course, it's not good because, again, we have an expectation value of R0, okay? So this is 0 as in point, which one was it? B, right? Okay? And again, we violated the rules in this case, so that's why we're not going to keep this case. And the last case, if I tried to work it out, I would end up with W, and then I would have W, R0, W, R0, and a bracket. Okay? You would have R0 acting directly on phi 0. Okay? So this is again 0 as in A, okay? Or similar to A. Okay? Here we have R0 acting on phi 0 on the left. Here we have R0 acting on phi 0 on the right. Okay? Can't work. Okay? So you see from all these cases, 5 cases that I tried in a naive way, obviously, only one survived. This one. Okay? And you can see that these rules make sense. Because if you try to violate them, you always run into the problem of R0 acting on phi 0 really. Okay? And that makes no sense. Okay? Because we know that R0 acting on phi 0 gives you 0. Of course, you may ask yourself the question, do I have other terms? Because, I started with surrounding one operator in each case with brackets. Well, what if I try to surround more? You see, I can't do it. If you really look at what would I have to do, okay? I would have to say, so I have, say, I'll just sketch it, but I will not really follow this through because, this is really not going to produce anything meaningful. If I try to surround two operators, you see, you can try. You have to avoid this one, you have to remember. This one you have to avoid. This one you have to avoid, because the rule says avoid it. Okay, so you don't have to really play with those three. But you can surround, say, those two, because you will have R0 on one side. You cannot surround those two, you will have R0 on the other side. Okay, you can try to surround all three, but if you did, you would have R0s on each side. Well, can't do it, So you can see that I haven't done, there are no other terms. So I am done, there's only one term. How many brackets did I insert? Class? One pair. What the rule says about that? So that means R equal 1. Rule says that minus, the sign is minus 1 to the R rule, which is minus 1. And there is your third order correction to the energy, right? You see it here. The principal term, and that is your renormalization term. And we just worked out. Okay? This is fantastic, isn't it? You can do things in this simple way. I actually think that because of this, perturbation theory in high order should be taught for undergraduates. Maybe without telling, okay, the paper, is a paper that you need to prove, but I think to learn the technique is not a bad idea, because you can really suddenly enable people, right, and allow them to derive corrections to energy to very high orders without really, spending a lot of time, okay? Well, okay, so how about fourth order? Well, but before I go to fourth order, what I would like to do is, okay, let me try to explain these rules. I explained them so far through examples, but let me explain them now more carefully, not just through examples, but really trying to tell you why we have these three rules, 1 through 3. Okay? So, the first rule says, no two brackets can touch. Okay? So I'm going to look at rule 1. No two brackets can touch. If I wanted to have brackets that touch, I would have to have something like this. Okay, let me try to create a situation like this in a general order. Okay, I would have to have something like this. Okay, or that. Okay? Why? Because, the principal term has a very well-defined structure. It's WR0, 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 okay? It's always the W's mixed up with R0s. Okay? You never have W squared. Because you always have R0 resolvents between pairs of W's, if you want to have brackets that touch, that's what has to happen. You see, I would have to have brackets in this configuration or that. But you see, that is not going to work. Because in this case, this is 0, because if you try to have R0 acting on phi 0, you end up with a 0. Okay? Here, this is 0, because R0 acting on phi 0, or the cat phi 0 is 0. Okay? That's what this is doing. Okay? So maybe I'll mark it. Okay? So that's why we have rule 1. No two brackets can touch, because if they touch, you will have R0 acting on phi 0. How about the second case? Okay, why is it that so rule 2, we're saying there that bracketing of the leftmost and rightmost W, or W's I should say there, okay, is not permitted, okay? Well, let me try to do it. Let me try to actually bracket them. So what do you have? Remember, WR0, 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 that's what I'm dealing with here. So I have W, then maybe I run with some dots, I have another W, then I have R0, and I have the rest of the expression, okay? So if I tried to bracket the leftmost, I would have to put brackets in this way. Okay? That's what I would have to do. Of course, an alternative would be that I do it sort of in the right part of the expression. So I would have R0 here, then W, and then a bunch of terms, and W, and close it, and I would try this. You see, you can't do it. Why? Because if you try to bracket the leftmost or the rightmost W, your resolvent will suddenly have to be forced to act directly on phi 0. You see here? It will go right here. And in this case, resolvent will go right here. Okay, because this part is the number, you take it out. Because you take those numbers out, you again have a situation where resolvent, in this case, acting on phi 0 gives you 0. Okay, so this is a no-go. And then this one, when you take this bracket out, you have R0 acting directly on the ket phi 0. Okay, so once again, we are seeing that rule 2 has to be obeyed. Okay, what about the third rule? Sorry, I was talking about, no, this was, let's see, I think I mixed up the numbers. Note the brackets can touch, there was 1. Bracketing of the leftmost and rightmost, okay, that's 2, okay, so I'm fine. And then each bracket per must have W's, okay, well, we know it already, right? That is obvious, so if I say go to rule 3, okay, let me do it here, perhaps. Okay, so maybe I'll keep that for future reference. Okay, so rule 3, of course, if you try to the rule 3 really is a sort of related to the fact that if you try to violate it, you would end up with, you would have a situation where you have, say, R0, right? If you didn't have W, okay, in our expression, you would have to do this, okay? And then it doesn't even matter what the rest of the expression is. That is 0 because, once again, R0 acting on phi 0 is 0. And, of course, you could have an alternative scenario where your brackets have, say, R0 here and then W. So even if you have W here or W here, okay, as long as you don't have a W here or there, you are getting an expression which is vanishing, right? So in other words, you can see that that's how these rules are what they are, okay? So equipped with this knowledge, let's work out the problem of the fourth order. I am going to keep what we got before from our previous considerations, and let's try to recreate these expressions from the bracketing rules. Okay? So, I guess, maybe I'll keep the rules, so we can always have a look if we need. Okay? So in the fourth order, well, the principal term is W, and then you have R0W, 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 and you finish, right? 4 W's mixed up with R0s. And now I'm going to start inserting brackets. I suggest, because you have to do it in your homework, that you first start with surrounding 1 operator, okay? So when I start writing, 1, 2, 3, 4 of them, okay? Maybe I'll use again red color to insert the brackets, okay? So you can see them. Okay, I'm bracketing this one, okay? In the next term, I'm going to bracket the next one. Okay? And that's all I can do in terms of surrounding 1 W, because the other W's are the leftmost and the rightmost. I'm not supposed to touch them. Okay? But of course, nothing says in the rule that I cannot do the following. I can also put 2 middle W's inside the brackets. Okay? That's okay. This one and that one. Okay? They are, you can see they are non-straddling, they don't touch each other, and they both have W on each side of the bracket. Okay? But, and that's as much as you can do within this expression, surrounding a single operator. Okay? But I can surround more than one. Okay? So let's write another copy of the principal term. I can certainly take the middle section here, okay, and surround it with the brackets as well. Because I have W's on each side, and I'm not using the leftmost or the rightmost. So that's fine. And there's nothing else I can do. Because anything else, if I try more, I will be touching the leftmost or the rightmost W's or violating the other rules, okay? So now all you need to do is to work this out. Okay? So what you do next, so in your homework, that's what you do. You first show me your work. You put your brackets in, and then you're going to work out the expression with the proper sign. So the proper expression here is, this is W, okay? Then you have W, R0, W, then you have, W, R0 squared, you can see squared, because if you take the W out, then you have R0 squared, R0 running into R0, then you have another W, R0, and W. If you look at the next term, it's going to be, again, you take the expectation value of W out, and you end up with W, R0, W, then you have R0 squared, W, and you close it, right? See W, you can see R0, W, then this one is gone, so you have R0 squared, W. And the next one, you have two W, so that's going to be expectation value of W squared. Okay, and then you have W, and now when you take these expectation values, terms in red, you end up with R0, 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 which is R0 cubed. Okay? W. And the final one, you take this bigger chunk, okay, which is actually second order correction to the energy, K02, and then you have W, R0 squared W. Okay? And the rest of the story is the signs. You just have to count the number of bracket pairs. Here we have one bracket pair, so that's a minus. Here we have one bracket pair, so that's a minus. 1. Now two of them here, so that's a plus. Minus 1 to the R rule, okay? So here, this one is, I'll write that as a plus so that you see the plus. Okay, maybe I'll also say here, R equal 1, R equal 1. This one has R equal 2, the number of bracket pairs. This one has also, it doesn't matter, so you count the bracket pairs, you don't look at how many operators they, incorporate, okay? So it can be a very long bracket, as long as it's a one pair, that's a minus. Okay, so here R is 1, so the sign is minus. Well, we can now enjoy it. Just look at what we got before. So we got the right expression, okay? You can see that these two terms are exactly the first two terms here. The next term comes with a plus, that's the third one here. And the last one is the last one, with a minus. Right?
Something is not right. What was the powers of R?
Sorry?
The third, you need it to the cube over there. I think this term is correct.
Which one?
On the left here.
Oh, yes, yes. Well, you see, that's not how good this is. Yeah, very good. Okay.
On the left.
No, it's
also.
the third term.
Yeah, third term. Yeah, third term. I thought I know. I'm probably said cube and something like this. Yeah. Okay, 1, 2, 3, 4, cube. Okay. Remember the rule. The number of the power, the total power of the resolvent must be n. Must be order minus 1. Okay. All right. Well, you see, good. So this is a good application of the rule. You can correct yourself. All right. Okay. So, well, then of course, the next order is fifth. Okay. So I'm gonna now erase. Yes, this correction had to be there. Okay. So I hope that this is registered. I will erase this now. Maybe I'll still keep this one. Actually, erase what's on there. Okay. Because we already explained the rules. Okay. So how about if I look at fifth order? I'm not going to do it because that's your homework. I just want to give you some pointers. So to facilitate your work on it. Okay. So how do you start your fifth order? Okay. You start with the principal term, which will have 5 W's. 1, 2, 3, 4, one more. 5 only. That's the principal term. Okay? Now you will start inserting brackets into it. My suggestion to you to organize your work always in each order is start surrounding a single operator. So this W, that W, this W. That's 3 terms already. Then start surrounding 2 single W's. So this one and this one, this one and this one, and this one and this one. That's 3 more terms. Okay? Well then, start surrounding more operators than, you're done with, well actually no, you can do 3. This one, and this one. Because you have 3 of them. So there's going to be another term which has 3 W's surrounded by brackets. Okay? And then you go to now surrounding more than 1 W. Okay? How can you do this? Well, you can see that there is this section. You can surround that. Or you can surround this. Okay? But that's not everything. Because once you're done with that, you can also surround those 2 and this one. Or those 2 and that one. Okay? That's also you can do. The rule set does not tell you how many brackets. You can introduce as many bracket processes as you can squeeze into it. Okay? So then you're done with surrounding, all cases surrounding 2 W's. Okay? And maybe 2 W's and 1. And then the next case will be surrounding, try to surround more W's. Well, we have room for this here. Not in 4th order, because in the 4th order, if I tried, I would have to run into the leftmost or rightmost. Here I cannot, I can still do it. You see, there's this whole section here. I can surround that with brackets. But as I said, and watch out for this, because otherwise you're going to miss 1 term. You can also put bracket inside the bracket. Okay? The rules, I did this. I see you have the rules. Did I say you can do it? If I didn't, then you can. Right? Okay? And if you think about it, actually, that makes a lot of sense. I'll actually comment on this. Because these 3, okay, if you bracket them, okay, that's the principal term to 3rd order, actually. Okay? Which means that if you put an extra W here, that's going to be the renormalization term 2 in 3rd order. And you remember where these renormalization terms come from. I said they come from these K0 contributions, K0M contributions to W prime, to that shifted W that we developed, right? So obviously we expect that the higher order corrections will have lower order corrections in them. Okay? Some people actually call it a super bracketing technique. So instead of using the Huby's brackets, okay, you would use these sort of curly brackets. Professor Paulus has this mentioned in his notes, okay? Well, then they really work out like the brackets, except that you don't put brackets inside the brackets because every curly bracket represents already all possible brackets inside it. Okay? I'm not going to spend a lot of time on it because it's really one of those, little polishing statements on top of what we already did. Okay? But please remember that you are allowed to put brackets inside brackets, as long as you don't violate these rules. Okay? So you can imagine that if I go to higher orders, I have more and more of this stuff. So the final comment I would like to make about the bracketing is the wave function corrections. Okay? Because you will also be doing wave function, 4th order. So let me try to briefly explain this. Rules are the same. Really, so I'm not going to really, I'll just say wave function, right? But I will not really spend time deriving these rules or commenting on them too much. Again, because they're obvious. We follow the same set of rules. Non-straddling brackets that cannot touch. Now, the second rule has to be modified because it says the bracketing of the leftmost and rightmost is not permitted. Well, we don't have a leftmost. In wave function, our principal term, okay, in the wave function, principal term is, so the principal term in nth order in general, okay, is R0 W to the n V0, right? So there is no leftmost W. So, but you still cannot touch, you still cannot bracket the rightmost W, okay? You don't have the leftmost, so you just have to modify rule 2 a little bit. And then rule 3 applies as well. Each bracket must represent the mean value with W's on each side, okay? And you can put, of course, brackets inside brackets if you have enough space to do that, okay? So let me show this on some orders, let's say 2nd order. I'm not going to do 1st order because you remember 1st order has only R0W, so there isn't enough room to do any bracketing in it. But for the 2nd order, I have R0, W, R0, W, phi 0, that's the principal term, okay? And then I need renormalization terms. So let's sort of work this out. Okay? You see, I am, again, you start with surrounding one operator, one W, with the brackets. I can do this here. But then I'm done with it, you see, because I cannot surround this W. Okay? And I cannot do more, because if I try to do more W's, then I'll have to touch the right post, right? That means that I would force the resolvent to act directly on phi 0. Can't do it. So there's only one. R here is 1. So the sign is minus. And that means that if I start writing the renormalization terms here, it will be minus W. And then you have square of the resolvent W phi 0. Okay? That's the renormalization term. Okay? And if you look back, you look at our notes, you see there. So let's look at one more. Okay? Get you as close as I can to your homework problem. Okay? So what is the third order? Again, the principal term in it is R0 W, R0 W, R0 W phi 0. Okay? That's the principal term. Now we have to figure all the remaining terms. Okay? So, you write your principal term on the side. Okay? And then you start putting brackets in it. Okay? So we can surround single W's this one. Or the next one. But I cannot surround the third one because I will be touching the right post W. Cannot do it. Okay? So I have two of those. But then I can of course do more because I can also surround two single W's with brackets. Okay? So this one and that one. And then I can make an attempt to surround more. Okay? Which is more operators, more W's. Okay? Can I do this here? Well, yes, I can. I can simply take this part and put it inside brackets. Okay? And I cannot do more because if I try to, do say, these three, I can't do it because I will be touching the right post W. And if I try to do more work, of course, I will be failing with the rules. So I'm not going to do this. So the conclusion is now that what are our expressions? So here we have R equal 1, here we have R equal 1, here we have R equal 2. I'm counting the brackets now. Okay, and here we have R equal 1. Okay, so if you start writing our expression, maybe I can now erase the rules, then what we have is this. We have psi 0, 3. The principal term is, of course, R0 W cube phi 0, right? And then the next term has R equal 1, so it counts with a minus. Maybe I don't know, I can write it with red, maybe, so we can see the renormalization terms. So the next one is minus expectation value of W. You take it out, and then you have resolvent running into another resolvent, so that's R0 squared. Then you have W, R0, W phi 0. Okay? Then you have the next term, which also has expectation value of W, so actually, that looks ugly. I'm going to open the square bracket here. Okay? And then I will have plus R0, W, R0 squared. W phi 0, okay? That's the next bracket there, right? You can see that if I take this W out, then I have R0, W, R0 squared, W. Right? So that's what I did. Then, and the next term is plus. There are two bracket pairs in it, so minus 1 to the R factor is plus. So it's expectation of W squared, and then you can see that if I take these expectation values out, you have R0, R0, R0. So that's R0 cube. W phi 0. And finally, the last term comes with a minus again because there's a single bracket pair, so it's W, R0, W, and then we are left with R0 squared W phi 0. Okay? So now we've got all the renormalization terms in second order. Okay? Double check that I didn't miss anything. Yeah. Okay, of course we've seen that expression before, but now you can see how quickly I can get it. So when you go through fourth order, you do exactly what I did here. Remember that you can put bracket inside a bracket. Don't miss that. Okay? Because you'll be forcing me to take some fractional strange points out of your whatever small number of points that you can earn anyway in this, right? So I don't want to do it. I just want to give you all the points. And okay, all right. So, and you can see, of course, that these rules have a beautiful structure also. You remember there was this relationship that, you can always double check your expressions. Because you always remember, and I really encourage you to do this. Nth or n plus first order correction is phi 0, W, psi 0, n. So if you work out, say, fourth order, okay, so I'm going to do the, if n is 4, if you put fourth order here, then it's going to be fifth order. And it means that if you work out your fourth order wave function, you have to simply see the same set of terms in your fifth order correction to the energy. The only difference between them will be there will be an extra phi 0 W in front at each one of them. Okay? So that's your good verification procedure. Alright? In case you wonder, did I miss anything? So I will sort of do them in parallel in a way. Right? Okay? Alright. So now we're done with sort of this part. I did have a break today, but we started also late. So let me just finish with some comments and then we're done for today. Okay? So, is this all clear? The bracketing, because that's your homework problem, right? So I want to make sure. Okay.
Is there a way to work, so using that relation is clear, how to get to kn plus 1 from psi n? Is there a way to work backwards from kn plus 1?
Yeah, remove phi 0 w.
It's just not clear, I guess.
Well, you have to be a little bit careful, yeah, but let's go, do I still have it? I guess did I keep it? Yeah, not really, I guess. Maybe, I don't know. Somewhere in this. Yeah, well, there's a little bit of it, right? You can see that all I need to do, you have to look at this, yeah? So you would simply be taking the w's, right, in each case, right? So you end up with r0 squared as your leading term. You see that makes sense. You see there's r0 squared there?
So just the right one?
Yeah, that's right. You just take the, sort of this part. You start taking them out, right? And so on, right? Of course, you kind of have to remember that, in this case, you wonder which one, this one or that one, right? So you have to kind of watch, you have to, in a way, you have to know where they come from. So you don't touch things that came out of from the inside, right? You touch what was in the principal term. You are removing W phi 0 in the principal term, right? Part of the expression, not what came out of this removal of brackets, okay? Those brackets removed are not untouchable, okay? Yeah, so then you can do it backwards, yeah. Yes, that's a good question. Please, of course, remember all these things. Those are little things you have to, if you pay attention, you really, the chance of making an error is kind of pretty much none, right? And this is something you can write a computer program for anyway, so I will do probably. Okay, all right. So if you write one for the homework, I guess I'll give you some extra points, as long as you can prove to me that this works correctly. All right. Okay. So now we're back in MBPT. Okay? We want to now go back to MBPT. We have all the knowledge now, deep knowledge of Rayleigh-Schrödinger perturbation theory, good enough to study MBPT. Okay? As you remember, in MBPT, we are interested in solving the Schrödinger equation, okay, for the non-degenerate, in our case, non-degenerate state psi naught. We write the Schrödinger equation in the normal ordered form. Where Hn is defined as H minus the expectation value of H in phi 0, and delta E0 is the energy, total energy of a system minus expectation value of the Hamiltonian in phi 0, where phi 0 serves two roles. Phi 0 is the unperturbed state, okay? So it's a 0th order approximation. This is ugly. Approximation to psi 0. But in our case, because we are in the many-body context, phi 0 is an independent particle model state. Okay? So phi 0 is also a Fermi vacuum. Okay? For many-body considerations. Okay? So in other words, in the case of MBPT, we want to solve the Hermitian eigenvalue problem where Hn is our operator K. Alright, so this is, if you want to phrase it in terms of what we're talking about in perturbation theory, okay? Trying to obtain psi naught, the non-degenerate state psi 0, which is typically the ground state, and the corresponding eigenvalue K0, which is the difference between the total energy and the expectation value of it, which, as I said, is a correlation energy. Particularly, this, strictly speaking, if phi 0 is the Hartree-Fock state, then this is a correlation energy. And phi 0 is simply an independent particle model. I used that acronym, I think, before, IPM state. So it's a single state determinant. Okay? So we are simply assuming that we can write our wave function, maybe I should say, as a structure where a single determinant phi 0 dominates. Okay, that's going to be our unperturbed state, and then we have various corrections in first and higher orders, okay, that originate from particle hole excitations from phi 0. So the whole role of MBPT is to learn. How can I learn about various particle hole excitations out of the independent particle model state phi 0, okay, single determinant that I choose as a reference, using perturbation theory, okay, as a sort of a mathematical means to do this, okay. So obviously, this means that we have to define a few items to get ready for perturbation theory. Okay, we have to sort of do some preparations. Okay, we have to choose phi 0 properly. Of course, because you have to remember, I don't know psi 0, I am computing it, so I have to choose phi 0 wisely. Okay, so there must be a discussion here how to choose phi 0, the single determinant. Okay? We know that phi 0 will be a single determinant, meaning that it's going to be a determinant, say, spanned by some single particle states, spin orbitals P1 through Pn, which you can write in second quantization as xp1 dagger through xpn dagger acting on the vacuum. But the question will be, which single particle states? You have to sort of have some idea where do they come from. Okay? Because depending, you have to remember, if I know psi 0, then it's easy. Then we don't have this class, because we already know it. The purpose of MBPT is to calculate it approximately, because you will truncate your MBPT expansion at some order. Okay? So you have to have some good idea about what is the good choice of phi 0. And you can see that this depends which spin orbitals. If I have said, I give you spin orbitals, you have to tell me which ones you're going to pick up. And then the second thing will be, how do you generate them? Okay, you have to generate them such that your phi 0 that comes out of it is the dominant configuration in your expansion that you are trying to calculate. Okay? So it's not a trivial question. But there is more. We want to use perturbation theory. So we want to split. We want to split our operator Hn, which is K, into the unperturbed and perturbed parts. Perturbation into the unperturbed part and the perturbation. And in doing so, we have to do it such that our K0, okay, then we know all the spectrum of K0, the entire spectrum of K0. We need to know all eigenstates. Okay? Among them, there is phi 0. So when you choose your phi 0, okay, you have to make sure, or maybe I should say, once you choose your phi 0 and K0, you have to make sure that the determinant you chose is an eigenstate of K0. Okay? That's a constraint. We have to work the problem. we have to choose spin orbitals defining Phi0 such that it not only is a good approximation to psi 0, but it also is an eigenstate of the unperturbed part of the Hamiltonian. Okay? So this is going to be our next task. So maybe I'll just finish, because I'm done with it today, with this, a little comment. Well, we know the Hamiltonian. We know the Hamiltonian, with the original one, not the HM, is Z plus V. Let's assume that we're going to be dealing with pairwise interactions, okay? The most common case. We know how to write Z in second quantization. Sum over PQ, P little ZQ, XP dagger, XQ, right? We know how to write V. Suppose I write it with in a sort of Goldstone style. Okay, so we have XP dagger, XQ dagger, XSXR. Okay? So, with a given spin orbital basis or single particle basis, I can define these operators. Okay? We know the little z, we know the little v, so it is very tempting to say, how about if you just split h in this way? And then, of course, you would have to split hn, but hn is easy because you just subtract an expectation value, right? It's tempting to say, how about if I just treat z as my unperturbed problem and v as my perturbation? Well, that's the biggest mistake you would ever make. Okay? Because v, okay, if you're, nuclear people will laugh right away, because they know very well that interaction is a strong interaction, it is massive. Okay? It has to be so strong that it can hold positive charges together, for example, right? So obviously, that is known. For chemists, may say, well, maybe Coulomb law, maybe this is a soft force, it's not so bad. No, it's also big. Big enough that you cannot do it. That kind of perturbation theory will never converge. So what we have to do, and that's going to be the beginning of the next class, really, we have to figure some approximation to the V, which is a one-body operator. In other words, our unperturbed problem, once I start working on the K0, I have to define it in such a way that it is a Z part, obviously, it must be there, but also some sort of a one-body operator which effectively accounts for two-body interactions. You already probably feel what it is. It's going to be the sort of, for example, the mean field of Hartree-Fock would be a good choice, right? Because the potential in Hartree-Fock already accounts for electron-electron, for example, or interactions, right? In some way, it's an approximate way, but it's the interaction is already there, and it is a one-body operator. Remember, Fock operator is a one-body operator. So certainly there will be one good choice. So we'll talk about these choices, okay? So please, you can see that MBPT is not like some other perturbation theory. It's some, like people do harmonic oscillator and then do anharmonic correction. Well, that's easy because you have an exactly solvable problem, harmonic oscillator, that you correct for anharmonicities. Okay, that's natural. Here, it's not so natural. You have to think it over. You have to come up with the proper definition of perturbation in the unperturbed problem, and then once you have it, then you know what we'll do with perturbation? It will be just k minus unperturbed. We will not spend, so the way you do it is you don't try to predict a priori what perturbation might be. It's going to be total operator minus the unperturbed. So we'll focus on unperturbed, we'll properly design it, and then we'll simply subtract it, and then we'll know the perturbation, and we'll see if the perturbation operator has some sort of a nice structure that we can deal with. Okay? So it's the different kind of a theory in that sense, right? Compared to, say, some textbook examples of perturbation theory that people use. Okay, so I have to stop here. I guess I'll see you on Friday. So hopefully you have now all the information about the homework, right? If you have any questions, just but I hope it's good. Okay. Thank you very much.